Hi everyone, we are Group 3. Today we are going to introduce Convolutional Neural Network, CNN. For today's agenda, we are going to explain how CNN works and where to apply it in real world. Also a model demonstration to give you a little taste. What are convolutional neural networks? Let's briefly talk about artificial neural networks first. An artificial neural network, or ANN, works like a simplified model of human brain. Each neuron receives signals, processes them using learned weights, and passes that signal onto the next layer. If we feed a raw image directly into ANN, the number of parameters becomes extremely large. For example, a 100 times 100 color image already contains 30,000 pixel values. Fully connecting all of them causing slow training, overfitting, and it loses the spatial relationship between pixels.
Let's start with how we humans work. When we see an apple, our eyes scan for specific features, the round shape, the small leaf, and the red color. Our eyes then send these observed features to our brain. The brain puts all this information together and concludes, that's an apple. This is almost exactly how we teach a computer to see a picture. The entire process is managed by a convolutional layer, which is built to mimic this idea of scanning for features. The computer doesn't see an apple, it sees an input matrix, which is a large grid of numbers where each number is a pixel value. Next, instead of an eye, the computer uses a filter. It's a small matrix that defines the area it can see at one time. Every value inside this filter is a weight. These weights are what the model learns. As the filter scans, it extracts features and builds a new matrix called map. So how does the filter scan? Let's walk through the math. First, the filter overlays itself on top of the input matrix, covering a small patch of pixels. Each weight in the filter is multiplied by the pixel value it is currently overlapping. Second, add all of these values together and don't forget the bias. Now we have the sum, Z1, putting into the feature map. You might be asking, what if the filter hangs off the edge? To solve these, we use zero padding. The grids that are outside the original image are multiplying by zeros. Then the filter slides over one pixel to the right, we call it stride of 1, and the entire process repeats to get the next value, Z2. After the filter slides through the entire image, we will get a complete feature map. A single filter only detects one specific feature, so we apply a set of filters to find many different features, and each filter creates one unique map. The stack of maps is the final output of this convolutional layer. This stack of maps means we have a huge amount of data. This data isn't just expensive to process, it also makes us vulnerable to overfitting. This is where pooling layer comes in. Pooling makes the map smaller while strategically retain the most important information. There are two common methods of pooling. We have a feature map from last layer and a 2x2 pooling filter, so this filter observes a 2x2 group of pixels at a time. One method is max pooling, where the filter keeps the greatest value of the group and put it in a new smaller map. The whole map is complete after the filter slides through the original map. The other one is average pooling. It slides in the same way, but instead of finding the max, it calculates the mean of all the values inside the filter area. These average values are then put into the new map. Let's put all the pieces together. This is the complete architecture of a convolutional neural network. Here we only show one set of a convolutional layer followed by a pooling layer, but in a real model you would typically repeat the set for multiple times. After passing through the final pooling layer, we flatten the maps into a single vector. Then we feed this vector into fully connected layer, similar to ANN we mentioned at the start. It looks at all the evidence and puts them together to decide on the final output. Now, computer can see the picture and know what it is.
We will now see some typical applications of CNNs. The first example of CNN is image classification, where the model assigns a single label to an entire image. For example, a CNN can distinguish dogs from cats by learning visual patterns such as edges, textures, and shapes. This is used in photo tagging, content moderation, and visual search systems. A second application is object detection, which not only identifies objects but also locates them in the image with bounding boxes. This is, for example, essential for self-driving cars, which must detect pedestrians, traffic signs, and other vehicles in real time. A third important application of CNNs is medical imaging. CNNs are widely used to analyze X-rays, MRIs, and CT scans to spot abnormalities, for example, detecting tumors or identifying lung infections. They help medical personnel increase accuracy, reduce interpretation time, and thus support early diagnosis.
We will now show the model demonstration. In order to see its applicability, we train a convolutional neural network model using the Python programming language. The goal of the model was to perform image recognition on a dataset containing 16 different classes of flowers. The CNN was designed to automatically learn important visual flower features from the input images and be able to classify the new flower images into their respective categories. Now I will describe the steps that we followed to create and train the CNN model. We began by downloading the dataset from Kaggle, which contains various images of 16 flower classes. The data was then split into 3 datasets: test, training, and validation, to ensure proper model evaluation and prevent overfitting. The test dataset is used to teach the model and contains the dependent variable, namely the flower class. This means that the model learns patterns, features, and relationships between input images and their corresponding labels. The validation dataset helps the model to improve and generalize and is used during the training, but not as to update the model. It acts like a checkpoint to ensure how well the model is performing on unseen data while it's still learning. The test dataset is used after the training is complete as a model evaluation on unseen data, and thus it helps to evaluate the final model accuracy and reliability. When training the model, we want it to learn to recognize patterns. Therefore, we applied data augmentation to the training dataset to make the model see different versions of the same images, like flipped, rotated, zoomed in or out, or changing brightness and color. This helps the model to learn general patterns instead of memorizing exact pictures, so it performs better on new images. For the validation and test datasets, we only used simple transformation to keep the images as close as possible to their original form, like resize to make all the images the same size, to tensor, converting images into a format that the model can understand, and normalize to adjust the brightness and color range to be consistent across all images. This keeps the images consistent and evaluates the model fairly without adding any random variations. After that, we define the CNN model and train it for 40 epochs, meaning we ran it 40 times and every additional step was learning from the previous one. It is important to mention that the running took a long time, namely approximately 1 hour and 10 minutes. Once the training was complete, we performed predictions on the test data, and conducted a prediction analysis to understand model performance by plotting the accuracy curve and visualize the training process. Finally, we visualize the predictions and create confusion matrices for both test and validation datasets.
Looking at our performance, the model achieved an accuracy of 81% on the training data, and it performed even better on the validation set, scoring 87%. We can see a sample of individual predictions from the test set. GT stands for ground truth, which is the correct label, and PRED is our model's prediction with its confidence score. As you can see, the model performed well, correctly identifying multiple flowers with high confidence. For instance, it identified sunflower with 100% confidence. However, we can also spot misclassifications. For example, a bellflower was classified as a magnolia. This confusion matrix gives us a complete overview of the test set's performance. The bright diagonal line shows all the correct predictions. For example, the model correctly classified 89 instances of tulip. The off-diagonal cells show us where the model got confused. For this set, we got 87% accuracy as well. The fact that our test set performance is similar to the validation set performance suggests that our model generalizes well to new unseen data.